Okay, so in this lesson, we're going to be finding the volumes of 3D figures, and these three figures are going to have been formed by taking shapes whose boundaries are defined by functions in the xy plane and revolving those shapes around the x or y axis or other lines to form a three-dimensional object. Now this is the same thing that we were doing in the last lesson. We called that one also volumes of revolution, and we called it the disk method. We're going to be using a slightly different method, but very similar, what is called the washer method here. And as we go through our first question here, we will see what the difference is between the disk method and the washer method. But to begin with, let's just sort of recap a little bit of what we were doing with the disk method. We ended up at the end of it with this formula here for the volume of a solid of revolution using disks. And let's keep in mind, or let me just highlight something in here. If I write this, just bringing the pi back inside the integral, like this, what do the elements of this formula here mean? Well, if we go back to our disk here, remember that our disk had a thickness that we called delta x, and it had some radius that was given by f at x or by y in this diagram here, and we put those together to get sort of the volume of an individual disk was, pi, I guess I'll use y here, squared times delta x. Okay. And then this, of course, pi y squared is the area of the circle that forms like the top of the disk. And this delta x over here was the thickness. Okay. Now, then we took the limit as n goes to infinity, so we made our, we had more and more and more and more disks, so our disks got thinner and thinner and thinner, and as n tended to infinity, our sum turned into an integral. So what we have over here in the integral is we have this section right here, which represents the area of our disk, or I guess we should now call it the cross-sectional area. Well, let's say the area of the cross-section. Okay, which is still our circle. It's still pi r squared. Okay, but that means that this dx here has to represent the thickness of our disk. But by making n go to infinity, we're basically making our disks thinner and thinner and thinner. So they are now sort of what we might call infinitesimally thin. Which makes basically they're almost infinitely thin, but somehow when we add them all up or integrate over them, we still get a finite volume. Okay, so this volume formula is basically an area, okay, an area of a circle, or the cross-sectional area of the shape that we formed, integrated from one end of the shape to the other. And we're going to be using this same general formula both in this lesson and in the next lesson. So let's take a look, sort of introduce our first question that we're going to look at here, and then we'll look at why the method that we use for this one has to be different from what we've done before. So in this problem, we are going to revolve a region that is formed by the intersection of two curves. So we're asked to find the volume of the solid generated when the region enclosed by y equals x, so that is our blue curve, and y equals x squared, which is our red curve. And this is revolved around the x-axis. So we're taking this area in here enclosed by these two curves, and we're forming a volume of revolution by revolving this around the axis. So what you can kind of imagine here is that this is not going to be a solid sort of shape. This is going to have an outline, and then there's going to be kind of this cavity in the middle of it. It's going to be hollow on the inside. So let's sort of zoom in a little bit and think about how we can adjust our method for finding volumes to accommodate this. So here I've just zoomed in on that intersection between that region, that area that's contained in between the two curves. So let's imagine that we are doing the same thing that we did in the last lesson. we're taking like one of these little rectangles that represents our area, and we're going to have it rotated around the x-axis just like we did before. So it's going to come sort of around kind of like this. And let's have this like this. Okay, this is going to have some thickness here, delta x, but we're also going to have the shape that it forms here is going to be kind of a hollow little shape. Okay, we're going to have an inside and we're going to have an outside. So this part, we'll sort of shade this in over here, is going to be part of the solid of revolution, and this part in the center here is just going to be empty. Okay, so the cross section of our solid that we form here is going to have kind of this hole in the middle. Okay, so let's kind of zoom in and take a look at what that cross section is going to look like. Okay, it's going to look like this. Okay, instead of being a solid disc or a solid circle, it's going to be a washer shape or a ring shape. And if we want to calculate the area of this cross section, which is what we were sort of integrating to get our volume, the area we want is sort of this area in here like this. Now, how are we going to calculate that area? Well, we need to calculate the area of the outer circle. Let's just say our area here is area of this outer circle minus the area of the inner circle. And to calculate this, we're going to need two radii. We're going to need the radius of that outer circle. So I'll just label that in blue, and we'll call this our outer. And we're going to need the radius of that inner circle. I'll label this in red. We'll call that our inner. So our inner and our outer radius. So the area of our outer circle is going to be pi r outer squared. The area of the inner is going to be pi r inner squared. Now, how in our problem here do we get the radius of those inner and those outer circles? Well, the radius of the outer circle is going to be from here up to that upper function, that blue function there. And then our inner radius is going to be from the same point, that point axis of rotation, up to that inside function there. So that blue line for us is going to be our outer radius. And the red line, again, is going to be our inner radius. Our outer radius is just given by the value of the function x, because that was our blue function, y equals x. And our inner radius here is just going to be given by the value of the function x squared, because that was our red function in there. Okay, so let's kind of put this together to solve the problem that we were asked to solve. So find the volume of the solid generated when the region enclosed by y equals x and y equals x squared is revolved around the x-axis. So we're going to set up the area of our washer or our cross section. There's only one O in cross section. We know that this area is going to be pi of our inner radius, sorry, our outer radius minus pi times our inner radius for our washer squared. And we know that our outer radius is going to be given by, if we're looking at a sort of a particular point in our revolution here, this is our outer radius, which is going to be given by the value of the function y equals x. Okay, so in our diagram here, the outer radius is given by our sort of our upper function. The inner radius is going to be given by our lower function, because our inner radius is going to be right in here, our inner, which is given by x squared. So let's put in those functions into our cross section here. So our outer radius is given by x squared. Our inner is given by x squared. So if this is the area of our cross section, to get our volume, we are just going to integrate this from one end of our shape to the other. And what are we integrating? Well, pi x squared minus pi x to the power of 4. We're integrating with respect to dx. And the limits of integration in this case, we can just get them off the graph. Our shape starts here at x equals 0, and it comes over here to x equals 1, so that's going to be from 0 to 1. So sometimes you can read these off the graph if they give you a graph of the region. Other times you would have to find the points of intersection between the two functions that they give us. So from here, we can just evaluate this integral. The pi, we can bring that out in front. 0 to 1 of x squared minus x to the power of 4 dx. And from here, it's just a straightforward integral. We need our antiderivative. And this antiderivative is going to be evaluated from 0 to 1. When we evaluate it at 1, we are going to get 1/3 minus 1/5. When we evaluate it at 0, we are just going to get 0. So just simplifying this, we're going to have 2 pi over 15 is our final value for the area. Okay. So we're less concerned about the final answer here. We're more concerned about, in general, how do we apply this method? So in general, our volume is going to be our integral from a to b. I'm just pulling the pi out in front of the integral. And we're going to have some function, f at x squared, minus some other function, g at x squared. And we're integrating with respect to x. And this function f at x is going to be, let me make sure I get the colors right here. It provides our outer radius, or our upper function. Okay. And our second function, g at x, is what supplies our inner radius, or our lower function. We're thinking of them in terms of the top or the bottom function. So this sort of general expression here is what you're going to need to be able to use when this object, or the volume, or the solid formed by your revolution has a space in the middle of it. Okay. Now, sometimes the space can be caused by another region, because we don't always have to revolve this thing around the x-axis. Okay? So sometimes they'll give us a question where we're revolving around a line that is other than the x-axis. Like in this case, we are asked to find the volume of the solid formed by revolving, again, the same region enclosed by the same functions, but we're changing the line here from the x-axis to the line y equals 2. So if we can sort of visualize what would happen here, we're going to have this little area element in here, and this whole thing is going to get rotated kind of around like this. Okay. So I'll just take this off of our diagram here. So what we're going to have to do is we are going to have to think about if, let's put this little element back on here. Okay. This is sort of the direction we're revolving these things. We know that in order to figure out the area of our cross section, we need our inner radius and our outer radius for this washer that forms our cross section. So because like our line has shifted to, it's like in the previous question, the axis of revolution, the line that we're revolving everything around was below this area in terms of y. The blue function, x, was our outer function, and the red function, x squared, was our inner function. So we've switched this around now because we are revolving everything in the opposite direction. So now the red function is our outer function, and the blue function is our inner function. But the radius, the expressions for our radius, is a bit more complicated than that. So let's take our inner radius first, which is going to be this distance right in here, our inner. So that distance, if we want to think about it in terms of the value of the function x, but the value of that function x is this distance here from the x-axis up to that blue line, up to the function y equals x. So the distance that we have that is our inner is the distance up to the green line minus that distance in the function. So our expression here for our inner radius is 2 minus x, okay? Because 2 is, like this distance here is 2. Okay, so 2 minus x is going to give us that inner radius. Similarly for our outer radius, which is all the way down to here, our outer, okay, the value of the function x squared is this distance right there. So our outer radius is going to be 2 minus the value of that function, so 2 minus x squared. So what's our volume going to be here? Well, it's going to be pi. Our integral is going to be that outer radius, 2 minus x squared, all squared, minus that inner radius, 2 minus x squared. And we're going to integrate with respect to x, so over dx. And our limits of integration are going to be the same as they were in the previous question, because that, that region still starts at 0 and it still ends up at x equals 1. So we're still going to integrate from 0 to 1. Now this is a little bit more complicated expression, but before we start to evaluate this integral, let's expand and simplify what we have inside of our integrand here. So expanding the first bracket is going to give us 4 minus 4x squared plus x to the power of 4. And expanding, let's just do the 2 minus x times the 2 minus x is going to give us 4 minus 4x plus x squared dx. And then we can simplify this by collecting some like terms in there, I think. So the 4 and the negative 4 here, because this negative sign gets distributed to all these terms, of course, those are going to cancel out. We're going to have negative 4x squared minus another x squared, so negative 5x squared, and then still an x to the power 4, and then a I guess, a positive 4x integrated with respect to x. Okay. And now we just have to evaluate the integral. We need our antiderivatives. So we're going to have x cubed, a negative 5/3. This would be x to the power of 5. We need a 1/5 out in front. And then an x squared with a 2. Evaluate this from 0 to 1. And just like in the last integral, when we evaluate it at 0, it's all just going to be 0, so we just have to evaluate it at 1. And doing a whole bunch of calculator work gives us the answer here, 8 pi over 15. So more important than this final answer for the volume, though, is sort of what does this mean in general for our method here. So in general, if we are revolving about some line x equals, we'll call this x equals h here, our volume is going to be pi, again, integral from a to b, and our expressions in here for our inner and our outer radius are going to be some function f of x minus h, and our other function g at x minus h, and we're integrating with respect to x. Okay, where again, this f at x is our, again, let's, the colors doesn't matter because we switched the colors. So this f at x is sort of our outer function. This is our inner function. Okay. Now, when I set it up, this question above, and I got up my expressions for my radii expressions were opposite to what you see in the brackets here. So rather than the function minus h, it was h, which was in our case 2, minus the function. So 2 minus x, or 2 minus x squared. The order doesn't matter because of the squaring in there. So however you want to think about it, it'll work equally well. So we'll just sort of put a box around this. Something that we're summing up. Okay. All right, we'll look at one last example here. What happens if they ask you, again, instead of giving you a horizontal line to revolve everything around, they give you a vertical line. So the same region that we've been looking at all along, find the volume of the solid form by revolving the region enclosed by y equals x and y equals x squared about the line x equals -1. So we now want to treat this as an integration in terms of y instead of in terms of x. So our little area element or rectangular element that we think of revolving around is going to be horizontal instead of vertical. So we want to think here in terms of what is our inner radius going to be and what is our outer radius going to be. So the revolution is going to go around that line here. So our inner radius is to here, and our outer radius is all the way out to there. So our outer function is the function x squared. Our inner function is function x in there. Okay. Now, we need to think of these things, though, rather than functions of x, we want these to be functions in terms of y. So let's take our two functions, y equals x, and write them as functions in terms of y. So y equals x is pretty easy. This just becomes x equals y. So this is, just x equals y. So this is our function in terms of y. For y equals x squared, we are going to have to rearrange this a little bit. So let's take the square root of both sides. So root y is equal to x. Okay. And so our function here is x equals, y to the 1/2. Now, when we do this root, we have to consider both the positive and the negative possibilities here. But we only want the positive one, because when we look at our graph, we notice where is the region that we are rotating here. It is at positive y values. Okay, so we don't have to consider both the positive and the negative parts of this function. We just want the positive one, all right, which is this one, sort of this part sort of over here. Okay, so we've got our two functions here. Let's think about what our inner and our outer radius are. Our inner radius goes from x equals -1 all the way up to the value of the function. So it is going to be -1 minus, and the function that we're interested in is that function y. So -1 minus y. Okay, or if we okay, I'm going to change what I'm doing here a little bit just so I'm consistent with the formula that I wrote on the previous slide. So on the previous slide, the formula that I used was the function, which would be y, minus the h value, which was the number associated with the axis of rotation. So it'd be y minus -1 in this case, y plus 1. Okay. What I had written before was correct, and when you square it, they'll both work out to the same expression. I just want to make sure, I think in the interest of clarity, that I just follow that formula. So, so for our outer radius, then we are going to have the same kind of thing. What is our outer function? It is the y to the 1/2 function, and then we're going to subtract, again, -1. So y to the 1/2 plus 1. Now we can put all of this together into our volume expression. So it's going to be pi, it's going to be an integral. Our outer radius squared, so y to the 1/2 plus 1 all squared, minus our inner radius, y plus 1 all squared. We're integrating with respect to y, and our limits of integration are still going to be from 0 to 1 in this example. Remember, those are now values of y in this case, but I set this up as a really simple example so that they basically didn't change. So now we're going from, let's put it, sort of do it like this, from a y value of 0 up to a y value of 1. Okay, and that's where our limits of integration come from. Okay, now we can expand and simplify before we go ahead and evaluate our integral here. So y to the 1/2 times y to the 1/2, when we're squaring this, we are going to get y plus 2 y to the 1/2 plus 1 minus, if we're squaring this thing in the second part, in the second bracket here, y squared plus 2y plus 1, integrating with respect to y. Do we get anything in here that is going to cancel out? It looks like these 1s are going to cancel because we're subtracting them. So our integral is going to become pi, the integral from 0 to 1. Let's see, 1 minus 2y is going to give us a -y. 2y to the 1/2 will still be 2y to the 1/2, and minus y squared dy. So we need our antiderivatives here. So when negative 1/2 y squared a y to the 3/2, we're going to need a coefficient of 4/3 to give us the coefficient of 2, and then this would be a y cubed, and we need a 1/3, and we need to evaluate from 0 to 1. Okay. And again, doing a whole bunch of calculator work in here, we end up with a final answer for the volume of pi/2. Okay, but in general, though, we're more concerned about sort of the way that we approach this. So we could say that in general, if we're sort of revolving around a line y equals h rather than x equals h, our volume is going to be pi times the integral from a to b. We're going to have some function of y minus h, some other function of y minus h squared dy to get our two area elements. And again, this is going to be our outer function, and this is going to be our inner function. Okay, so this sort of expression here is completely analogous to the one that we had on the previous slide when we're doing our revolution around a line that was horizontal.